everybody, and welcome to online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. And this is lecture number 32 which we are talking about, and the lecture topic is DIBL, GIDL, channel length modulation, source drain series resistance, part 2. So, we will start from where we have left in the earlier lecture. We had finished understanding the threshold voltage roll off and also the concept of punch through, the short channel effect. Let me now come to each one of them individually and explain to you. So, this is basically, if you look, a two-dimensional contour plot of a MOSFET, right. So, this is basically a two-dimensional. When I say two-dimensional potential plot, the two dimensions are x and y. So, this is, let me assume this to be as x. So, let me assume this to be as x and this to be as y, right, and x is from therefore say source to drain, and y direction is from gate to the bulk, the body. What is the third dimension? The third dimension is actually within the gate. So, looking from top till the bottom through your screen of the laptop, from this end to the back side of the device, that we are not considering at this stage, and does not make sense to consider at this stage is because the most of the potential which you are giving is at the gate potential and the source potential on the drain side. Source is generally grounded. You do not give any potential on the back side of the device, right, or the laterally back side of the device, not at this one, the back side of the device. Therefore, the most of the study which you get is a two-dimensional study which you get for all practical purposes. Now, if you look at the device dimensions, so the first device which you see on the left hand side is basically a long channel MOSFET, and on the right hand side what you see is basically a short channel MOSFET. So, this is basically short channel and this is long channel. The discussion of short and long has already been taken care of in the earlier classes. Now, long channel MOSFET, if you see very carefully, these dotted curves are equipotential plot lines, these dotted curves. These are the points which have equipotential as you move from source to drain. Now, what we have done is that we have amplified this part and shown it here, and as you can see here, as you move away from the interface down below, the value of the voltage goes on decreasing, which is true also. So, your surface potential is 0.45, which is just near the silicon dioxide interface, but as you go down you reach to a value which is approximately 0.05, almost. So, this is the edge of the depletion, almost to the point where it is actually hitting the body, right, and therefore, that is 0.05 which you get. Now, and as you can see on the right hand side, if you look at this point carefully, the value of the voltage at this point, this is the first point is well within the drain region, and that is the reason it is almost 3.85, right, because just 0.15, assuming that 4 volts have been given, only 0.15 has fallen in terms of voltage drop, and then you get 3.05, then 2.05, and then it goes down as 1.05 and 0.85 as you go down from top to bottom. The potential at those points, these are not surface potentials, these are potentials which you see here, right, and this is expected also as you move from top to bottom, almost like a potential divider. Let us do the same homework or the same work on the right hand side picture. Here you see that the potential which was initially very flat throughout the channel length of the device, here the dimensions are so small that now you do have a problem. The problem is that they are not straight now, which means that when it becomes straight, it basically means that my d psi dx is almost equals to 0, which means that my electric field in x direction is 0 when my VDS is very small or my channel lengths are very large. However, if you go to the right figure, because of the short channel effect, they are not constant, they are varying, and therefore, there will be an electric field which is available to you. So, there will be an electric field in the horizontal direction, but there will be also an electric field in the vertical direction in this case. So, you will have Ex as well as Ey electric field here. So, this slide was to show to you that because of these two electric fields, the contour plot changes for the potential plots, right, and these are constant potential contour plots shown on the left and right for a long channel and a short channel device. This gives you an idea that yes, not only physically, but actually it is true that the electric fields are much larger in case of a short channel devices. So, as you can see, in short channel devices the constant potential plots are curvilinear, and therefore two dimensional electric fields have come into picture. And therefore, as you can see, both x and y component of the electric field are there in the short channel MOSFET, both x and y. And since it is curvilinear, it effectively means that it is again position dependent. I will explain to you how is it. So, if you look at this graph here, then if you concentrate at this particular point, not only not only my d psi is changing with respect to dx here very steeply, very fast, but if you move from this side to this side also, there will be a change in the value of the potential, which means that the absolute value and its differential changes for the potential, right, and this gives you the curvilinear plot. If you give a fixed gate voltage, I am giving a DC bias, not an AC bias, and I am giving a DC VDS value, then for a given gate voltage, higher band bending takes place at the silicon dioxide interface in short channel devices as compared to long channel devices. Because short channel devices, you have also scaled down the value of Tox. When you scale down the value of Tox, the electric field in the transverse direction increases, because if you remember your Dennard scaling law theory, then my Tox also scales down by a factor of k. Right? When it scales down, the electric field in the y direction, which is basically epsilon ox by Tox, will actually go on increasing, which means that Ey goes on increasing. The electric field in the y direction goes on increasing. You tend to have therefore both the electric field equally high in case of a short channel devices. Okay. So, you can see the last point, that in a short channel device, the source drain distance, the distance between source and drain, is obviously comparable with the MOS depletion width in the vertical direction, and the source drain potential has a strong effect therefore on the band bending over a significant portion of the device, which means that since in short channel you have brought the drain very close to the source, the drain is able to control the activities towards the source end. So, understand this point, that we are bringing things closer. When we are bringing things closer to each other, the drain is able to talk very easily with the source, and will be able to influence the source potential to a larger extent, or what is happening at the source end can be influenced to a larger extent very easily, right. So, with this let me come to the next effect after threshold voltage modulation, and other effect is drain induced barrier lowering, and referred to also as a DIBL or DIBL effect, drain induced barrier lowering. This is a short channel effect where the threshold voltage of a MOSFET decreases as the drain voltage increases. Remember, we had a discussion in the previous class where we said that when VDS equals to 3 volts, my threshold voltage roll off was much higher as compared to when my VDS is equals to 0.1 volts. So, when you are in the saturation region of operation, your roll offs are much higher as compared to when you are in the linear region of operation, and that is why the reason is, this is what the reason you can actually also understand. So, let us look at the energy band diagram as you move from source to drain. Let us suppose this is the y direction which you are looking into. This is the gate region. Let me assume this to be as the gate region. This is the source and this is the drain, and you are applying a fixed bias on the drain with respect to source. So, what we are doing is that VDS I am applying, which means that I am applying a drain voltage minus Vs, since Vs is most of the time 0, therefore, I get VDS to be equals to V, and this is the energy band, electron energy band diagram. So, let us go one by one as we move ahead. So, what we see is, if on the drain side, if you apply a positive bias, the electron energies will actually go down, because it is minus q times energy is equals to minus q times V, and therefore, you will see that the energy levels will go down, correct. What will happen is that the energy levels will go down, and therefore, if you see the right hand side energy band diagram, this is the conduction band edge which I am showing it to you. At low VDS, this is the value, at high VDS it shows a much larger drop is there, which means the difference between the pre and post becomes very large. And let us look at the source side. So, when the source side, what I have written is q times V built in minus Is. Why? V built in is the sort of the potential barrier. V built in is primarily the potential barrier which the electron has to face across the depletion region to move towards the channel, that is V built in. And why minus psi s? Because as you make the voltage on the drain side higher, you tend to reduce the band diagram, the conduction band diagram, it goes down, and as a result you see the delta Eg or the change in the value of the barrier comes. As it happens, more and more charge carriers can go into, which effectively means that since the band has actually fallen down, you can afford to have a lower gate voltage to form the channel, correct. This is the concept of drain induced barrier lowering. What has happened here is that it is V built in minus psi s when you apply a voltage. When you did not apply any external bias, when VDS was low, you see that these are perfectly aligned with respect to each other, you see they are almost straight line alignments are there, which means that it is just the built in voltage which is there. Now if you put VDS value, there is a minus psi s coming into picture. This minus psi s implies that the band will be lowered by a factor of del EB. So del EB will basically, del EB is the lowering value which is there. So higher the value of VDS, more is the drain induced barrier lowering. But then there is a limitation to this DIBL effect. The limitation is that you cannot increase the value of VDS beyond a point, because that will imply hot carrier effect. There will be large second order effect which will be actually compromising the reliability of the device. So that is one thing you should keep in mind while doing the DIBL effect, right. And this DIBL effect's overall effect on the device performance is that the threshold voltage goes down, and you can understand why it goes down. The same thing has been written here in a much more detailed manner. What we are doing in long channel device, the gate has a better control over the channel, right, and therefore in short channel devices the drain electric field also significantly affects the channel, which otherwise would not have effective in a short channel device. When a high drain voltage is applied, when you apply a high drain voltage, the barrier, as I discussed with you, the barrier height is lowered, and therefore further decrease of the threshold voltage takes place, again discussed with you, and threshold voltage has been lowered in this case, right, and threshold voltage is getting lowered. The value of, so if you plot ID versus VGS, gate to source voltage, for higher values and lower values, you see what is happening here. Now the slope of ID versus VGS is almost the same, which means the subthreshold slope might be almost equal, but the effective value is much lower in case of a lower value of VDS, right. Let me come to gate induced drain lowering, right. Now when you apply a gate voltage, right, when you apply a gate voltage, you are effectively adding more and more positive gate voltage, assuming n channel MOSFET I am assuming, and I have an enhancement mode MOSFET, I go on increasing the gate voltage. What happens is that it tends to positive voltage, it tends to lower the energy band at the gate side, right, keeping source and drain almost the same. Now because of this you have got two types of effect. One is the gate induced drain leakage, one is, so if you reduce the dimension of TOX, for example, there might be direct tunneling between the gate and the channel, there may be direct tunneling. Why? Because your oxide thickness is so small, electric fields are so large that you are able to pull the electrons from the inversion layer. Then you can have two types of tunneling, which is BT-BT, which is band to band tunneling, and you have got gate induced drain leakage. I will come to BT-BT later on. Let me explain to you what is gate induced drain leakage. What happens is that as you tend to reduce your gate voltage, the current starts to fall down, right, and then that is expected also if you plot. This is a log scale of ID. However, at very low values of gate voltage, and if you reverse the gate voltage, you see the current suddenly shoots up, and this current is basically the leakage current which you get, and this is primarily because of the gate induced drain leakage. Why? Because the gate voltage has become so large, it is actually affecting the drain side and trying to make the drain side conduction band go down. As it goes down, the current further increases, and that is the reason you see the current increases. Then you have got the BT-BT, which is band to band tunneling, which you see here. Let me explain to you what is band to band tunneling. Now if you look on what we have plotted on the left hand side and on the right hand side, when N plus regions or N and P are very heavily doped, you will have band to band leakage. So typically those MOSFETs where your source drain regions are very heavily doped, N plus plus region, you can have a BT-BT, right, and that is what basically is band to band tunneling. I will explain to you, try to explain to you what is the band to band tunneling. Look at maybe let us see this graph, this one. I have this N plus region here, I have this N plus region, I have a gate voltage I am applying, source drain is always there. So, if you see source without any, if you do not apply any bias, they will be perfectly aligned with respect to each other. This is the Fermi level which you see, intrinsic Fermi level. This is the blue color is the Fermi level which you see, and this is the valence band, conduction band. So, as you can see, both on the source and drain being N plus region, my Fermi level is very close to the conduction band edge, very close to it. Now, and at the gate side, since it is a p type semiconductor, if you see, this is very close to the valence band edge, right. So, this is a p type channel, this is N plus source and this is a N plus drain. Now, that means that as you go on increasing the bias potential, or as you go on increasing the bias potential on the source and the drain side, you end up having a larger and larger sort of potential, variation in the potential. Now, let us come to the right hand side figure. If you apply either a negative bias or you apply large amount of positive bias, the band bending will take place, and what will happen effectively is that this band will get aligned with the conduction band, right, and as a result you will have a large carrier flow taking place between source and drain. This is known as BT-BT tunneling or band to band tunneling, right, and this band to band tunneling is responsible for giving you a large concentration of electron in the valence band. So, what happens is that you have let us say an area which is having almost very large value of charge carriers, and in other area the charge carriers are almost 0, they are not available. But if they are separated by a very small distance and if the band alignment takes place, then there is a high probability that electrons from a high concentration region will jump onto the low concentration region, and that will result in what is known as a BT-BT tunneling. This is known as a band to band tunneling. And another example of GIDL is this one, where we have shown you the current density because of GIDL is this, and the major contribution of GIDL is that off state power leakage or the standby power leakage is relatively high, right, and becomes very large in this case. Similarly, if you look at the right hand side figure for example, and if you make your drain voltage very high positively and your gate voltage negatively very high, let us suppose that then this is 0, the electric fields in this direction is in this direction. However, since VDS is equal to 0, there is a strong electric field in this direction. So, 2 dimensional electric field are available on the drain side, and if there is a EHP generation within the drain region because of some this thing, then what happens, the holes which are generated will be rushed towards the p type substrate, or it can even go to the oxide layer. But the problem with the oxide layer is that if it is very thick, you will never have the gate leakage current. There will be a body current which will be flowing. So, that is known as a leakage current, and that is given by this formula here, where ES is the electric field, effective electric field, A and B are constants. So, if you see the left hand side and right hand side, this is where you applied a positive gate bias and this is a negative gate bias, and therefore, you see the reverse direction of the charge carriers which are happening, right, and this gives you a brief idea about the gate induced drain lowering. We have already discussed channel length modulation to a larger extent earlier, just I will touch and go in this case. Now, if you look at very closely here, what we have done is that as the VDS value increases, this depletion thick will increase because of the reverse bias saturation, and therefore, this blue side will go on reducing, and that is basically delta L. And therefore, if you look down, that the VD sat is VGS minus VTH. Sat, why? Because this is the point where the velocity is getting saturated. So, if you plot ID versus VDS, so this is the point which corresponds to this point. So, that voltage at VDS where this happens. So, when the inversion layer tapers exactly to the drain edge, we define that to be as a saturation, right. And you can see that as the value of VGS goes on increasing, the value of VD sat also goes on increasing. Why? Because as the value of VDS increasing, electric field increases, and therefore, you need to have a stronger overdrive voltage to saturate the channel. And this is the concept of the channel length modulation phenomena, and effectively what we say is that therefore, in short channel devices with increasing value of VDS, my delta L value goes on increasing, as a result my L effective goes on reducing and my current goes on increasing, and therefore, the behavior of the device at saturation is bias dependent, which was initially independent of the bias, right, and it is modulated by the drain to source voltage. And therefore, you see L effective is basically L minus LD, where LD is the depletion width and L is the actual length of the channel. We have already seen that XP, the depletion width extending in the P region of a PN junction diode in the 0 bias is this much, and if you apply a drain to substrate bias we get this. So, as you can see, the space charge region defined by delta L, delta L is the width of the depletion region eaten away by virtue of a VDS being applied, will not form until and unless applied drain to source voltage is greater than the saturation drain to source voltage. So, as long as you do not apply the drain to source voltage more than the saturation drain to source voltage, you will never get the value of VDS. Okay. Now, as I discussed with you, delta L area, if you look, is nothing but the total space charge width minus the space charge width that exists when VDS is equal to VDsat, right? That is what is delta L. So, delta L is given by this formula here, right, and it depends upon many factors, but primarily on the value of del VDS. It also depends upon the VDS sat is obviously changing with respect to VGS minus VTS, and del VDS is equals to VDS minus VDS sat, and therefore, the current actually increases by this factor, that ID prime is the current, the absolute value of the current by virtue of the change in the value of channel length is given by L minus del ID into RD, where ID prime is the actual drain current, ID is the ideal drain current, and delta L is basically my channel length modulation effect, L is my channel length which is happening. This is the value of the current at absolute value. Let me come to the last part, and this is source drain resistance. Till now what we were assuming is that if you draw the source drain, and this is basically my contact, let us suppose, then I was assuming that there is no resistance between this point and this point. However, in reality this is not true. There will be a small resistance between these 2 points. Similarly, there will be on the drain side, and similarly if you extend this on the source side, you will also have contact here, and there will be a this is known as source resistance and this is known as the drain resistance. Because obviously because of finite silicon resistivity, and metal also will have some contact resistances. In long channel devices, obviously as compared to other resistance, this resistance will be relatively small, and therefore I can afford not to take it. However, in short channel devices, this forms a parasitic resistance and can be therefore be relatively a large fraction of the total channel resistance, right. And what it does therefore is, in reality, is that it tries to make the actual drain current go down. It will degrade the drain current compared to long channel devices, and that is what happens in case of a source drain resistance, series resistance effects in short channel devices. So, if you take series resistance into consideration and we find out the channel resistance RCH is given by obviously VDS applied drain to source voltage divided by the drain to source current, comes out to be this particular point L by whatever is written here. V on is basically V threshold in this case. The sheet resistance of the MOSFET channel rho CH is given by 1 by mu effective into epsilon ox into EOX. EOX is the electric field across the oxide layer. And for most of the technology, EOX max or the maximum oxide thickness is approximately 2 to 5 megavolts per centimeter. After this, there will be shorting and there will be direct tunneling between the gate and the substrate. And similarly, rho CH min means the minimum value of the resistivity is given by 2000 ohms per square for N MOSFET and 7000 ohms per square for P MOSFET. Now, quite interestingly, if you see therefore that the sheet resistivity of the MOSFET channel rho CH depends upon the value of mu effective, which is the effective field mobility. If the electric field mobility is much higher, what you will see is the rho CH will go down, right, and that is also one way of looking at it. Many researchers across the world and many industry have converted silicon to silicon germanium, where effective mobility is much higher because of strain technology, and that lowers the value of rho CH. Once it lowers the value of rho CH, I ensure that the sheet resistivity of the MOSFET is small, your currents are higher for the same applied value of biases, right. So, what we have known, this effect tends to degrade the resistance of the source drain region, right. With this, let me recapitulate what we did for this lecture. In this lecture, we looked into the second order effects, which is basically DIBL and GIDL. We also looked into source drain resistance issue and the channel length modulation effect. So, we looked into DIBL, right, we looked into GIDL. Within GIDL, we also looked into BT and direct drain current modeling. We then went to understand CLM, channel length modulation, and then finally ended up with source drain resistance. And most of the time these are all sort of a degrading phenomena to the second order phenomena, relatively degrading in terms of power, performance and area. So, with this let me thank you for your patient hearing. We will meet in the next class. Thanks.